So our speaker problems with the Zoom, so I invited him back to speak again today. So it's Anubhav Chaturvedi, whose name I probably mangled again, and why it's empirically or perhaps operationally incomplete. Okay, off you go.
Thank you, Mark, for letting me have a reattempt at this. I'd really like to run this through you because I work on fringes of foundations and applications. I'm from University of Dansk. I work in Marcin's group, which is the cybersecurity group at this new institution, ICTQT. And earlier I was working in National Quantum Center in the adjacent town in Sopot. So this, as you'd recall, this is about a new notion of classicality, a realist notion of classicality. Just a second. Okay. So there is this paper by Matt and Lorenzo, which is called Operational No Fine Tuning. And what it does, it gives you an insight into how the different notions of classicality or the realist notions of classicality are connected. What is the common thread between them? So in my words, and not taking theirs, it's realist notions of classicality ascribe certain operational phenomenon are not fine-tuned realist spaces. And what does not fine-tuned means is that you put this operational phenomena down to the level of reality, which is to say that these operational phenomena must also hold when you have access to the state of reality. For instance, Bell's local causality ascribes no signaling correlations, a parameter independent realist spaces. So basically, I messed it up. This should be X, but this is Alice to Bob no signaling, and that should hold even. We believe that this is because this comes from relativity. This should also hold at the level of reality, potentially conditioned on potentially inaccessible states of reality. So, and similarly, generalized non-contextuality takes operationally equivalent stuff and ascribes ontologically identical counterparts to them. So what's happening here is you have an operational phenomena that you believe in, and you believe in it so hard that then you find it reasonable to push it down to the level of potentially inaccessible reality. And the common thread between these things is called the no fine-tuning principle. And I'm not referring to Harrigan and Speckin's version of no fine-tuning principle, but Lorenzo's and Matt's version of no fine-tuning principle. But if you look at these phenomena to which the notions of classicality ascribe a no fine-tuned realist spaces, these phenomena are in the common known, well-known notions of classicality, they are all empirically falsifiable. For instance, in the Bell's case, no signaling is empirical falsifiable in the sense that I can, if I'm an alien, I can come down and show signaling at a distance, and then the no signaling condition would be falsified. And similarly, operational equivalence, which translates to operational indistinguishability of preparations, can be falsified if I can show that these two preparations can be operationally distinguished. So empirical falsifiability is a criterion for what operational phenomenon deserve a no fine-tuned ontological basis. So this is the first way in which empirical falsifiability plays a role in notions of classicality. The second way in which empirical falsifiability plays a role in notions of classicality is in the consequences of these notions of classicality that could be put to experimental tests. For instance, it's well known that Bell local causality implies that the value of CSSH should be less than equal to 2, and this is referred to as CSSH. This is referred to as the CSSH inequality. And we then proceed to go to the lab and use quantum states to violate this inequality. And the violation of this inequality implies that if we take outcome independence for granted, it implies that your realist model must involve some fine tuning. Other than that, violation of the operational consequences of notions of classicality directly yield quantum advantage in a plethora of operational tasks. For instance, a violation of CSSH inequality implies quantum advantage in device-independent information processing. So the insight that I will then formalize in the rest of the seminar is that empirically falsifiable phenomenon, they play a double role in a twofold role in when it comes to notions of classicality. They are operational prerequisites of tests of notions of classicality, as well as operational consequences of the realist notions of classicality. And we'll see how empirical falsifiability, how can we use this insight to get some nice consequences. So as an operationalist, I can put on my operationalist hat, and as an operationalist doesn't care about what's inside the devices, but only cares about the statistics that appear as a result of an experiment. In particular, we'll be interested in very simple prepare and measure experiments, where we have a preparation device which has some label. It could be any label, P, and a measurement device with the label M. And the measurement device outputs another symbol, which is K. And we are interested in the probabilities of occurrence of an outcome K, given a preparation P, given a measurement M was performed on preparation P. What's important here, these preparations and measurements, they can come from arbitrary sets allowed in an operational theory. So an operational theory really gives you the set of allowed preparations and the set of allowed measurements. This is the only important thing that will come in handy later. So from this point of view, if you look at quantum theory just serves, or any operational theory for that matter, just serves a twofold purpose. Quantum theory in particular attributes density operators to preparations, which are matrices, and POVM to measurements, because we are not interested in the post-measurement state, so we can restrict ourselves to POVMs. And quantum theory makes predictions via the so-called bond rule, which is just trace of the density operators times the POVM. The realist take on an operational theory, or just realist models, ascribe probability distributions over a measurable space to preparations to model our ignorance or model the lack of precision in preparing the precise state of reality. However, at any single round of the experiment, the system occupies a single state of reality, lambda, which is an element of an arbitrary measurable space. And the measurements are modeled by readout functions or response schemes, or as we call them in classical communication, decoding schemes. So basically, they specify the probability of occurrence of an outcome K when you have access to the state of reality, lambda.
And clarification question here. What are these optics and antics? Are these just typos, or do you mean something deep by that?
Yeah. Oh yes. So this was supposed to be left as a underlying thing. So in operational theories, we don't care about what's getting transmitted from the preparation device to the measurement device. So we are only interested in the statistics, unless you make additional assumptions such as the dimension of the communicated system or something else. But for now, we don't care. And this is a fancy way of saying that something quantum's going there. And I have a personal viewpoint that state of reality and the way the ontological models are designed, they are like classical data. And so this is the antic. The rest of the scheme here is that the shadows represent what I can really do in the lab, and what's in between is something deeper or some insight into what's going on behind that I might not have direct visual or sensory access to. It's my thinking. Is it okay? It's just
I think Andrew is asking if you have a typo on this slide.
Sorry,
optics, or do you mean ontic?
Ontic. Yeah, that's a.
Yeah, thanks.
State of reality. Apologies. Okay. Yeah. And the realist can also make predictions, and the predictions for realist prepare and measure experiments are just integrating over our ignorance of which ontic state was prepared with respect to response scheme. What's important here, we can I'm gonna my results here are also gonna hold for quasi probability distribution instead of probability distribution. So the epistemic state need not be constrained to being positive for all lambda. It could be negative as well. And the response schemes essentially are constrained by positivity and completeness. Okay, so this is the first new thing that is gonna be new to people. It's I refer to I must define some properties of preparation. So given a set of preparations, I define a property of this preparation as the maximum value of a linear functional of a prepare and measure setup. So the maximization is over the set of all allowed measurements in an operational theory. So this quantity that you get as a result of maximization is only a function of the set of preparations. So it's a property of preparations. And it's an experimental or experimental statistic. So it's an operational property of a given set of preparations. So the key thing here is maximizing out the dependence of the measurements from this metric, of the dependence of this measurement of this metric. Okay, and these properties are empirically falsifiable, because if in experiment I obtain a higher value of this metric, then this implies that either the prescriptions of your operational theory or the operational theory itself is false, or something's gone wrong somewhere. So
can I ask a quick clarification question? Are you assuming in your definition that the measurements all have the same number of outcomes? Because
no, you can just take the maximum number of outcomes. And for now, I'm restricting myself to single measurement setups. So there are no multiple measurements here. Is it okay?
Yeah, but it's just the sum over, I'm wondering about the well-definedness of the sum over k here, because if you have different measurements, if your measurements have different numbers of outcomes, well, I suppose it can. All right. All right.
Yeah, then just take the maximum number of outcomes, and that should do the trick. I'll get back to it.
Okay.
Okay. And so going back to the insight, this is a class of operationally empirically falsifiable operational properties. Very similar in the sense that they could be empirically falsified to no signaling or operational equivalence, and so on and so forth. In quantum theory, evaluating such operational theories for a given set of density operators constitutes a semi-definite program. And if it's finite dimensions, such a program, for finite dimension, it's a semi-definite program. And I'll be only considering quantum systems of finite dimension here. And the program fulfills a condition called Slater's condition, so that as a result of the program, you get the optimal POVM as well as the global optimum always, because the states are fixed. So this is just optimizing over semi-definite matrices that are bounded by positivity and completeness.
Sorry to interrupt again. Can you tell us what this S on the left-hand side is again? I missed that. What is S?
Okay, so S is the property, is any property. It's a metric. It's a success metric, so it's coming from the communication side. And the superscript denotes the theory you're evaluating this property in. And what's contained in the bracket is the set of given preparations.
And the coefficients C, are they somehow given to you?
The coefficients C are specific to S. And so this is, for instance, a property. So you can, for any coefficient, any real coefficient, we can take them to be real for now. And any real coefficient, a set of coefficients would define one particular operational property.
Okay, thanks.
No problem. Okay. For a given set of probability distributions over the measurable space, I call not fine-tuned realist properties of such probability distribution as the same success metric, but maximized over response schemes, which are constrained only by positivity and completeness, not by operational accessibility of the response schemes. Because operational accessibility or restricted operational accessibility of response scheme is already some sort of fine-tuning. Nevertheless, such an optimization over response schemes constitutes a linear program, and a very simple linear program. And we can solve this linear program right away. First, we notice that we can expand over the summation on the outcomes, such that we have, okay, I'll just go ahead anyway. So as you can see, the second equation here, you have sums of the coefficient, a sum of X with the coefficient index with 1, with the response scheme with the outcome 1. Oh, sorry, the probability of occurrence of outcome 1 given. So for each lambda, you can decompose, open up the summation for K. And now one notices that the response schemes are constrained by positivity and completeness for each lambda. And so they form a convex polytope, with the extremal points being deterministic response schemes, and everything's for each lambda. So you can really choose the optimal response schemes by just putting the probability of the particular outcome K, which maximizes this term within the summation. Somehow my pointers, somehow it's not working. Just a second. Okay, now. So these terms inside this guy, sigma over X, the coefficient raised to the power, superscript X with the outcome 1. And such terms appear in this expansion, and one can choose the best possible outcome for the response schemes by just finding out which one's the maximum sum over X, C, this guy. So this guy just appears for each lambda inside the summation. So we have, so this way we can solve the linear program in the previous slide and have the optimal realist, not fine-tuned property. And this will come.
I'm sorry to interrupt you here.
Yes.
I'm really struggling to see where the non-fine tuning assumption is playing a role here.
Okay, this goes into that the optimization is over. It's like in your paper, the treatment of preparation non-contextuality. So it's when you optimize over response schemes that are constrained only by positivity and completeness, and not by operationally accessible, or not over operationally accessible subset of the response schemes, because that's the fine-tuning that I'm trying to distill in by the way of this notion of classicality. So because I'm just optimizing on all possible response schemes, not the ones that are operationally accessible as a result of some restriction on the ontological model. Does this make sense? It's like the same, it's exactly the same thing as preparation non-contextuality, because it could be that, well, models of quantum theory cannot be modeled by, there must be, the set of response schemes that quantum theory allows must be a strict subset of all allowed response schemes as a result of preparation contextuality.
So I understand that, but then are you at some point then going to assume that S lambda and SO have to be the same? That would be the no fine-tuning assumption.
All right, yes, that would be the notion of classicality. I'm just going to turn to that in a bit.
Okay, understood. Right. Okay.
Okay.
It's just I was confused because you're putting not fine-tuned here, but I think that is the no fine-tuning assumption. But, okay.
Yeah. So that's, so there's the notion of classicality, and then there is this common insight, which is no fine-tuning principle. And so I could call the entire thing no fine-tuning principle, but for now I kept it separate to compare it with other notions of classicality.
It's
Nevertheless, so now it's our turn to define a notion of classicality, and in this work I'm restricting myself to just preparations, but this could as easily be extended to measurements and transformations in the theory. But for preparations, operational theory or a fragment thereof is said to be empirically complete if for all possible sets of preparations and all possible empirical falsifiable properties, there exists an underlying set of probability distributions over some measurable space, no restrictions on the space except for being measurable, such that these probability distributions have corresponding properties. So they explain these empirically falsifiable properties. And this is embodying the insight that the other notions of classicality, they provide empirically falsifiable properties and ontological basis. So I just extended that, took it to its further extent. And we're going to see that how this plays, this gives us nice benefits. This is my notion of classicality. This is a generalization of an already published notion of classicality, which we did in our previous work with deviations. It's called bounded ontological distinctness, where we restricted ourselves to just distinguishability, as we just ported distinguishability to the ontological level and nothing else. So here we generalize that to arbitrary properties. And I think it's also a generalization of the operational no fine-tuning principle introduced by Matt and Lorenzo, because in their definition there, they have only equivalent statistics, but the statistics could differ by a measure or such functionals. And we must discuss if this is a generalization of the no fine-tuning principle. Anyways, putting it along with the other notions of classicality, empirical completeness ports properties of the form that I introduced earlier down to the ontic level. That means even if you have access to lambda, one believes if the theory is empirically complete, there must exist a set of probability distributions which explain the empirically falsifiable properties. So, okay. So now let me introduce some properties that we're going to play with and see the consequences. My property of choice is the only property that I'm going to introduce, and then use this to get other things, is set distinguishability. So basically, it's instructive to look at these properties as tasks or maximum success probabilities of tasks. And this particular task of set distinguishability is where the measurement party, say Bob, tries to guess. So Alice gets an input, an n with the label 1 to n, and then Bob has to get which m-member subset of n the input came from. So the property has the following expression. So you sum over all non-trivial subsets, m-member subsets of n, and then you sum over all members of that subset, and simply this is the probability of success in each round. Okay, but this is a very well-known this is a generalization of well-known properties. For instance, when you have m equals 1, this amounts to guessing the label of the preparation that Alice sends, and this is commonly referred to as the distinguishability of those preparations. And if m is n minus 1, this corresponds to directly, or 1 minus of this number is referred to as anti-distinguishability. It differs from papers. So this is a generalization of distinguishability and anti-distinguishability. It's called set distinguishability. The ontological, or the realist counterpart of set distinguishability is, again, there's a typo here. It's set distinctness, and not of 3 epistemic states, for n epistemic states. Apologies for that, but the set distinguishability, set distinctness for n epistemic state has this expression, which is, again, you maximize over all possible subsets, and then you maximize the sum of the epistemic states for each lambda for all possible subsets m. This follows from the solution of linear programs that we saw earlier. So this is the operational property. This is the not fine-tuned counterpart. And using this set distinguishability, I'm going to construct two other properties. But the thing, they are all made up of set distinguishability. The first property is called average set distinguishability. So you average over m, which runs from 1 to n minus 1. So all non-trivial subsets of the preparations, and you average out. So there is a 1 minus n coefficient appearing. The other property is average pairwise distinguishability. So in the lab, you have, say, n preparation devices. So you take 2 of them and you try to distinguish them, or Bob tries to guess which one of the 2 device has been used to send the preparation. And it's basically the average distinguishability of pairs of preparations. Okay, so now, as a consequence of this notion of classicality, and this is the main result, we can show that you can show that for any empirically complete theories, average set, and for any set of n preparations, the average set distinguishability should be equal to average pairwise distinguishability. So irrespective of the particulars of the preparations and irrespective of their number. So this should always hold. if the theory is empirically complete. And so this has to be contrasted with the CSSH inequality. This is an empirically falsifiable consequence of the notion of classicality I'm introducing here. Okay, so I really like the proof. It's it uses a trick from a book called A First Course in Probabilities. So, and here we'll also see why we do not need to restrict ourselves to positive distributions over the measurable space. It could be arbitrary. So the main ingredient for proving such equalities, I'm just going to do the proof for 3 preparations because that's the non-trivial case, is these in just a second, are these identities. They are referred to as minimums, maximums identities, or maximum minimums identities, or maximum maximums identity. So for any 3 real numbers, this identity holds, which basically is if you take the pairwise, the sum of the pairwise maximums, it's equal to the total maximum plus the maximum of 2 sums. So how can we prove it? We'll have an associated ordered list where A is the largest of the 3 numbers, B is the second largest, and C is the third. So as the right hand side here, the first term will yield A, and the second term, the maximum of 2 sums is A plus B. So this is 2A plus B. And the left hand side will have a pairwise maximum. So that will involve comparisons between A and B. I'll get A and C, I'll get A, and then B and C, I'll get a B. So I'll have 2A plus B there. So this identity holds for all real numbers. And I tried to check if this holds for all kinds of majorization relations, but I'm working on that at the moment. We'll see. So, as long as your epistemic states are for each lambda, they supply a real number. We can use the same identity for each lambda there. And now we can integrate everywhere over the ontic state space, over the realist space. And as a consequence, we retrieve this relation for any 3 probability distributions. So this holds for arbitrary probability distribution as long as the number's 3. So they are 3 in number, and then this thing will hold. And now I can use empirical completeness to port this relation from the realist level to the operational level. And such stuff, such identities could be generalized, and the generalization is there in the green right here, and for arbitrary n. And this is what I use to prove the main result. So I hope this gives you a flavor of the proof. And the rest of the proof is just based on this identity. It's very simple. So now we can demonstrate quantum violation of this thing, and quantum violation of this principle using the equalities, which would just basically say a simple statement that for certain sets of quantum states, there exists no set of probability distributions over measurable space that can explain these properties. And this is, in my opinion, well, a good reply. In my opinion, Einstein had the viewpoint of determinism behind his questioning of quantum theory as complete. In our treatment, we are comparing quantum theory over stochastic theories, which are generalized statistical mechanics-like theories. And so my incompleteness is with respect to probability distribution. So it's a more general form of incompleteness than what Einstein thought, but that's debatable. It's just pondering. Anyways, for the proof, I'll consider the Mercedes-Benz trait. These are basically states on a plane on the Bloch sphere, separated by a 2π/3 angle. And for these states, average pairwise distinguishability, and this is, you don't even need to write a semi-definite program. This is just, I think it's trace distance. You can use trace distance between the density operators to find out that this is approximately equal to 0.933. Whereas these things are, or any three qubits are at most distinguishable by probability 2/3. And in particular, the measurement that's shown in the figure distinguishes these preparations by probability 2/3. So you have a lower bound, upper bound, and then you have, that means their distinguishability is 2/3. And these states are completely anti-distinguishable. And so the term corresponding to anti-distinguishability is 1. In particular, this implies that quantum theory is empirically incomplete. And the difference between the two properties is a positive number, 0.0997. And this is a measure of quantum theory's incompleteness. What I have not included in this presentation is that I have NPA like hierarchies that do not take the dimension assumption. And with those hierarchies, I have a proof that up to numerical precision, the three states, the Mercedes-Benz state, maximally deviate from this, from the three preparation equality. Okay, now I'll do something controversial. This is controversial because somehow people are not thinking about this. I propose a realist model of quantum theory, which is called the rho-ontic model, in which the ontic state space is basically the space of density operators. So each quantum preparation is in one-to-one corresponding to the ontic state. So it's like not, it's a row complete model, what I'm describing, but you can extend it to rho-ontic model. Now, one notice is that a rho-ontic model is parameter independent. It does not violate no fine-tuning principle, nor does it violate generalized non-contextuality, because what you're giving up is the preservation of convex coefficients from the operational level to the ontic level. So there is a this is a classical model, and this is how my machine, my computer, stores quantum stuff. So it's really a legible interpretation. However, even this interpretation violates our notion of classicality. And because we have made no assumptions such as outcome independence or any composite systems, nothing of that sort, not even some preservation of convexity or agents information about mixings, nothing of that sort has been made. It's a simple thing. So, and I think this is, in this sense, the strict, there is no way back to classicality. Any realist model for quantum theory must be empirically incomplete. Absolutely no way. In our group, we are only allowed to do foundations if we show quantum advantage. And this is, and I work on the fringes. So any deviation from the equality will, for instance, if the pairwise distinguishability is greater than the average set distinguishability, one gets an advantage in such a task which task is designed to test pairwise distinguishability. Alice has 3 preparation and Bob has an input corresponding to a subset, a 2-member subset of that preparation. And Bob has to guess, this is a promised communication task. So it'll never happen that Alice gets 3, but Bob is asked 1, 2. So you can remove that by setting priors to the task. And the constraint is another communication task is the maximum success probability of another communication task, which is average set distinguishability, is restricted by some value P. So a deviation from the equality directly translates to quantum communication advantage in such a task if pairwise distinguishability is greater than set distinguishability. If the deviation is the other way, which can happen, I'll show you in the next slide that can happen. Then you get an advantage in the opposite communication task, which is you're trying to find out the maximum average set distinguishability. The success metric of this task is maximum average set distinguishability, but the channel constraint corresponds to the average. Okay, this is the constraint. This constraint must be without cross right here. Is average pairwise distinguishability is bounded by some number P. Okay. So one utility of this is that it's one utility of the equalities is that in this space of where you plot one property against other, the classical set is a one-dimensional line, whereas the quantum set has a spread. So this translates to very easy experimental demonstration of experimental demonstration of violation. So to somehow simulate that, I randomly sampled triplets of pure states and density operators, and all triplets of pure states that I sampled and all density operators violated this inequality, and especially 99.9% of them violated this or deviated from the equalities by a factor of 10 to the power, by a metric of 10 to the power minus 5, which is computational precision. And basically sampling instances of semi-definite programs, and the red line, or which appears pink, is because of my hierarchy of semi-definite programs, which is like NPA hierarchy. And furthermore, this thing shows that the equality can be violated both ways. The cool thing is qubits cannot violate it the other way. You have to go to qubits. So this row cross is a set of qubit states, whereas a row triangle, which is the maximal deviation because of the hierarchy as well, is the set of qubit states. And because I have the hierarchy, I can do more fun things, which is I can increase n and find out the maximal deviation. And so, but not precisely, because hierarchies have limitation, SDP hierarchies have limitation. So this is just evidence of increasing quantum deviation. So these are normalized success probabilities. So they all go from 0 to 1 on both sides. And so this is a legitimate increasing quantum deviation, and it might be used to push down epistemic overlaps, because yes, something like that. And also this translates to increasing quantum advantage with the number of preparation, which in other setups cannot be done, or is very hard to find such instances. The difference between classical and quantum success probabilities. Oh, I missed a point, which is that as we can think of in classical communication schemes, we can think of a de-leveled classical message omega, which is operationally accessible. That word should be operationally accessible, sufficient statistic for state of reality. And so one can so that means it's sufficient. Knowing the state of reality will not help improving the operational properties. So this implies that classical communications is empirically complete. So any deviation implies quantum over classical advantage, where D is not constrained. D could be arbitrarily large. So apologies for missing that. So there are more things as an implication because this embodies the insight, which is and every other notion of classicality ascribes not fine-tuned realist spaces to empirically falsifiable operational properties. This notion of classicality implies all other notions of classicality, especially preparation non-contextuality, maximal psi epistemicity, and the one that we introduced earlier, directly, and using Matt's connections that Matt had in his PRL, I think with Maruni. I don't remember which paper that was, but using his connections, we can show that this also implies cogent spec non-contextuality via preparation non-contextuality and Bell local causality, which means that any violation of any other notion of classicality implies empirical incompleteness of quantum theory. Not only that, the proof that I used in this presentation involves 3 preparations, and any setup, GPT theoretic, any generalized preparations that from a GPT that have 3 preparations, that fragment is always simplex embeddable. So that is always generalized non-contextual. So generalized non-contextuality cannot see the non-classicality that empirical completeness can distill. So it has more visibility as well. Now, the key part, or the part that I find the most interesting, that we have my complaint with other notions of classicality, it's a mild complaint, I'm not pushing it, it's that the operational prerequisites of the tests of those notions of classicality involve the operational phenomenon, but these operational phenomenon were zero measure because they involve operational equivalences. As Matt and Lorenzo, they write in their paper, the statistics must be equivalent. And so they are zero measure. And so people must do tricks or find ways or derive bounds or something to get to zero measure spaces for operational prerequisites. But the operational consequences there were inequalities, which are loose things, which are harder to violate as compared to equalities. Now we have inverted the situation where you can have any set of preparations, and you can perform tomography and find out what the operational properties are for any set of preparations. So it's not a zero measure. It's like it works for any set of preparations, and the operational consequences of this notion of classicality is a zero measure condition. So it's very easy to violate. And this suggests that something like empirical completeness can be used as a and the way it's defined can be used to formulate a resource theory of ontological or realist incompatibility of quantum theory, using the no fine-tuning thing that's going across notions of classicality. So I hope that this would lead to some sort of unification later. And so that's it for now. And I am very thankful to my co-authors, which is Deva and Marcin, for letting me explore foundations and funding agency that give me money. That's it. I'm up for questions, and I'd like to hear your views.
If you could raise a hand on the on Zoom, or just indicate. This okay, I'll let Kathagata go first before I
Hi, Anubhav. Can you hear me?
Oh, yes, I can.
Hi. Yeah, nice talk. I have one question. I I'm not very familiar with quantum foundations. Could you please explain what you mean by set of preparations?
If you have you have three, suppose you have n different devices, and those correspond to a set of preparation. They need not, preparation means a system is being prepared in a controlled manner. That's all. And controlled so as to the theory can ascribe it a particular mathematical object. So a set of preparations is like a set of density operators which model preparation devices.
So basically an ensemble, is that a correct way to look at it?
No. Is it? No. Ensemble has probabilities of occurrence as well as the different. So it's a structure. Set of preparations is a pre-structure to ensemble. We don't care about the probability of occurrence, so as to say, the probability of occurrence is a controlled variable, as Matt puts it in his paper. It's a controlled thing. So we can make different preparations with whatever probabilities we choose. We are just interested in the set of preparations. Imagine this like a device with different buttons on the top. And whenever you press a button, a physical system goes out, and this physical system is modeled by a mathematical object in your theory, which in quantum theory are density operators. And so you can decide when to, what the frequencies of pushing the buttons by yourself, and that would correspond to an ensemble. But this is just a set of preparations. Is it okay?
Good, thanks.
Yeah. Okay.
Okay, Andrew.
Yeah, I'd like to understand a little bit better. So I think the main purpose or the main finding is you claim incompleteness of quantum mechanics based on these set of criterions that are not satisfied in your work, right? And so as far as I understand is that your program is to put into these ontological states, I think you call them lambda, is that right?
Yes.
And then try to see whether the results of the theory, the quantum theory, can be put into that kind of categorization, right? And then you have a series of technical results that show that it can't. And so I guess one conclusion would be quantum mechanics is incomplete, I suppose, as that's your conclusion. But couldn't you also simply say that this program simply doesn't succeed, that trying to force quantum phenomena into a sort of this ontological box of underlying classical states is simply sort of a wrong view of how quantum physics works? Couldn't you just reject that premise?
Yeah, but that premise was rejected, I think, as with Bell's theorem. So what we are interested in finding, because to my eyes, these are the realist models, and the restricted models are unbounded. They correspond to unbounded amount of classical communication. So this is real quantum advantage. That is not comparing qubits with classical bits. It's arbitrary. So what we find out here from the foundational perspective is, where do we require fine-tuning in our view of reality? So that part I might have forgotten to put in the consequences of the violation. So this is in line with Matt's stuff. And so we want to find out where we'd like to fine-tune the models of reality, and any deviation from these equalities, which are the consequences of the notion of classicality, implies that there must be some fine-tuning involved. Particularly, there must be some restriction on the set of operationally accessible response schemes. So you cannot access all possible response schemes. You must access a subset of these response schemes.
Let me ask a clarification question. Now, when you say the words fine-tuning, to me, that means I have some parameter that could take a vast number of possible options. But I need that parameter to take on this precise value in order to have a successful theory of that thing. And so that notion of fine tuning, I didn't quite see how it played into this discussion. Maybe you could elaborate on that.
Yes. So once you have a deviation from the equalities, you are no longer, that means realist models that preserve these properties do not exist for the particular theory under consideration. But they cannot arbitrarily deviate from these equalities. They deviate by this wacky number right here. This is the maximum deviation from 3 equality that I've shown here. This is a very specific quantum number. This is akin to the Cyril-Simms bound, which you get the maximum deviation from CSSH inequality. So your realist model should somehow, and not conspiratorially, somehow naturally explain this precise amount of deviation from the equality. Once you have deviated, you can go all the way to have maximal deviation, which is, I think, it's a number, not this number. It's a greater number. But quantum theory just allows this much deviation. This is the maximum amount of deviation from, up to numerical precision, of course, from the 3 preparation equalities. So that particular amount, which is a rational, is it a rational repeating number? It's a real number. That particular real number must be explained by a model of reality, and that is fine tuning.
So what would change if that number were different? What would be different about physics if that number were not the same as it is? I think that's maybe the question of fine tuning that Andrew is trying to ask.
What would change if that number was different? Then I mean, we believe in quantum theory, this is the number. If there's, you can compare other theories with respect to quantum theory. If the theory has deviation from the maximal, I can give you a higher deviation than the maximal quantum deviation, or in experiment, you can show maximal quantum deviation beyond quantum theory. That means quantum theory is falsified. Is that?
Let me put it a different way. And so you said that because there is this gap between these 2D numbers, that these ontic or these ontic theories have been ruled out. And then you talked about this fine tuning of the model. But my understanding is that the model itself can't capture this. And so what are you tuning? So are you talking about the gap as a fine tuning?
For everything that exists, a realist model. That first thing to note is that everything has a realist explanation. It's just that what are the minimal requirements of those realist explanation? And
so, for example, in the Bell context, you can have, if you throw out locality, for example, you can have some kind of realist picture, like Bohmian mechanics, for example, if you wanted to.
Can I attempt to answer the question?
I would love that.
I think I know the answer. So what's fine-tuned? Basically, the assumption here is that, well, earlier on, in order to define the classical value of things, right? And so in order to remove that deviation, it has to be the case that you can't have all possible response functions. In order that you wouldn't notice the deviation between the properties of the quantum preparations and the properties of the classical probability distributions that differ. In a sense, it's a generalization of the idea of preparation non-contextuality, where it's the same thing there. In order to note inequivalence of the preparations at the ontic level, the response functions have to be set in such a way that they wash that out. And so here it's just sort of a generalization of that same sort of Make sense?
I think so. So it's not really a parameter you're fine tuning. It's sort of the level, what kind of assumptions you make. You
can think of the, and those are the things that have to satisfy a very sort of particular criterion to avoid noticing this effect.
Can you repeat that, Matt? You froze for a second.
Parameters of the response functions. The response functions are specified by a number of parameters, and they're going to have to obey, you know, a certain set of equations in order to avoid effect becoming operational, directly operational, right? So I mean, that's the thing that's being fine-tuned, and there are parameters there.
Thanks.
Okay. Are there any other questions in the room? Okay, let me just, I know we're over time, but let me just say one thing. Connection to the work that I did with Lorenzo, I'm not entirely sure what's more general than what at this stage. The thing that looks more general is the maximization that you're doing in the definition of a property. And obviously we didn't do that, but we do allow sort of arbitrary pre and post processing of the data. And yeah, I know you know that, but so I'm wondering if, I mean, obviously, like, it could just be that we should have allowed a bit more general notion of processing of the data to include things like this. I'm not sure whether it's captured by the notion that we have at the moment, but in any case, I do think, yeah, it's interesting to revisit those ideas in the light of this.
I am, in the long term, I'm aiming towards a resource theory, one single unified, and that might be something that I think you guys are also hinting towards in the paper. And
yes, I think that's the ultimate aim of this, right? So you define the notion of fine-tuning to begin with, but the aim is to try and come up with a resource theory of fine-tuning and understand its relation to quantum advantage in various tasks. So I think this is a helpful contribution. Please do send me, have you sent me a copy of the paper already? I can't remember.
I was just waiting on hearing from you if this makes sense, because I work in non-foundational surroundings, and so okay. now I will prepare. Thank you for your.
I think you will get some pushback from, because you know not everybody is you know necessarily understands the goals of this particular sort of sub-program, as it were. But anyway, I'm very interested to see the write-up of this when it's done.
Thank you so much, Matt. Thank you for your time and letting me speak again. I'm very grateful.
Okay, just one final call for any other questions in the room. If not, let's conclude. Thanks very much, Anubhav. This is just to remind everybody, next week's seminar is our very own Kai Wagel. So I will send out his title and abstract as soon as I get it, but that'll be next Monday at noon. Okay. So thanks everyone, and we'll see you soon.
Thank you, Matt. Bye.
Bye.